Hey guys, now that we have built our tool, we want to test it rather to its limits. We want to make it face complex problems and see how it fares. So what essentially we would like to do is we want to make our life a bit difficult. I don't know why we would do it, but still we choose to do it to see how this tool would help us. So in order to do that, we slightly refine our problem. So originally we had a static object and we imposed a force on the static object, and the atoms of that static object, the atoms that constituted the static object, it dislocated itself, and this was made visible by the permanent damage that happened to the static object. Now what we are now going to do is we are going to consider a dynamic object. The object is now moving at a constant velocity, and the force that is experienced by the object, particularly the atoms of this object, is dependent on both the position of the atom and also the velocity with which the atom is traveling. So if you consider such a problem statement as opposed to our previous one, when we have such a problem statement wherein the force experienced by the atom is no longer dependent on its position but its velocity, we end up having an expression like this. So what you essentially need to do is you need to replace your f of x with x of t, which is nothing but the position of the atom, and when you take the first derivative and the second derivative of it, you will get this term and this term here, that is this term and this term here, the term associated with A and the term associated with B. So when you solve this expression here, so essentially what you would end up having is you will end up finding the position of the atom when a force is imposed to it as the atom is traveling. So you have a traveling atom and the force is imposed on that atom. The force experienced by the atom, it depends on its velocity and the position. Now after you have imposed the force, what is going to be the position of the atom at a given time t will be the solution to this expression here. Now we will take the tool that we have developed and we will try to solve this expression here. Now we have an expression and each of these terms have their own coefficient. So in order to make it approachable, we divide the entire expression by a. You end up having such a form of this original equation. Now I can replace, because my b and a and c are constant, I can rewrite this entire equation as something like this. Replace my normal looking b's and c with a fancy looking b and c. So the fancy looking b and c is nothing but the ratio of b by a, and the fancy looking c is the ratio of c by a. So now my expression changes to something like this. So my expression now has not just b and a, or b and c rather, it's a fancy b and a fancy c. Now the equation that I would like to solve involves f of x, first derivative of f of x, and the second derivative of f of x. And when I solve this, my solution would be of the form f of x. And now I'm going to take the approach that I've developed, that is I begin by assuming that my solution is smooth. Now when I make that assumption, it allows me to express my solution as a power series. So I end up with this expression here. I have a problem, I have an equation that's associated with my problem. I assume that the solution of the problem is smooth. So therefore that allows me to express my solution as a power series. Now I take the first derivative of this power series and I arrive at this expression here. The power series of my solution, first derivative of that assumed solution, and then I take the second derivative of it because my original problem demands it. So I have now my first derivative and my second derivative and my original f of x. Now from our previous experience, when we have a second order ODE, we understood that the a0, it represents the initial condition when my x is 0, and my a1 represents the first derivative of my f of x and my x is 0. So if my f of x is x of t, which is position, a0 indicates my original position and a1 will indicate my original velocity. So it means these two coefficients have some physical significance to it, so I'm able to understand it. But all the other coefficients, a2, a3, a4 and so on and so forth, I don't know what they are unknown to me. So we tend to find this A2, A3 and A4 from our original problem statement. And in order to find that, we rewrite our original problem statement as something like this, and we equate our second derivative to that of our first derivative and the original function. We are equating our second derivative to that of our original function and the first derivative. In this case, we are equating it, or before we are equating it, we are multiplying it with the appropriate coefficients and then taking the negative sign here. So our original problem statement now gives us an equation where we are able to relate our second derivative, which is here, to that of the first derivative on the original function, and that we are able to do so by multiplying it with the appropriate coefficient, summing it up and taking a negative sign before the sum. And when we do that, we have, this will give us a series, a power series, and this will also give us, or this is already a power series. So this is already a power series, and the sum of these two will also give us a series. So basically we are then equating two series, and both these left hand side and the right hand side will be equal, considering that these are series only when the coefficients are equal. And that means I will be able to express my A2, A3, A4 in terms of my A0 and A1. This is something that I could expect, A0 and A1, A0 and A1, because my coefficients are to be equal. So when I take that understanding, equate my coefficients together, I can write my A2 as something like this, wherein my A2 is equal to B A1, that is multiplied with the coefficients. I am multiplying my fancy B with my first derivative of x, and my c with the original function f of x. I am multiplying my v with my first derivative of f of x and with my c with my f of x. So my A2 can then be related to that of b A1 and c A0. Now it is also possible for me to do the same for A3. Now A3 is expressed in terms of b, that is the coefficient originally associated, and A2 and A1. But I already have an expression for A2 which is written in terms of A1 and A0. So therefore my A3 can also be written in terms of A0 and A1. So basically I have written my A2 in terms of A0 and A1. Now I also have written my A3 in terms of my A0 and A1. Of course there are the coefficients, these four coefficients associated with the original problems involved in both these A2 and A1. Now I can do the same for A4. My A4 can be written in terms of, just by equating this two terms or two expressions in my left and the right hand side. I have my A4 which is expressed in terms of A3 and A2, but we have already found that my A3 can be expressed in terms of A0 and A1, by A2 can be expressed in terms of A1 and A0. So therefore my A4 can also be expressed in terms of A0 and my A1. So all the coefficients, all the so-called or the originally unknown coefficients A2, A3, A4 can now be expressed in terms of known coefficients A0 and A1, which are nothing but my initial, can be associated with my initial position and my initial velocity. Now if I am able to substitute all these terms here, all these terms, that is replace my in my f of x, if I am able to replace my A2 with this term and my A3 with this term and my A4 with this term here, then I will be able to arrive at a solution for the original problem here. So I need to replace my A2 with a term that involves A1 and A0, A3 with a term that involves A1 and A0, and A4 with a term that involves A1 and A0. Then I will be able to come up with my original solution, or my solution that I expect for f of x. Now the problem is this equivalence of my coefficients, that is for A2, A3 and A4 and A5 and so on and so forth, is not as straightforward as what we faced in our previous problem statements. Now the number of terms associated with these coefficients, they are not only associated with the original b's and c, but they also are associated with two coefficients A1 and A0. So the number of terms that are associated with each of these unknown coefficients of A2, A3 and A4 and A5 and so on and so forth, they increase and they become more complex. So when I substitute all these to my original f of x, and when I want to rather rearrange them and when I want to make a sense out of it, it becomes extremely complex for us. So even though my original tool that I have built is able to handle such a complex expression, of course, which has a physical significance, I face a problem in not using this tool, but rather in getting some sense out of the solution that I get, in making my solution a bit more elegant and a bit more approachable. So therefore, even though my tool still works, I want to make the entire solution a bit more easier. And that is what we will consider primarily in this session. The tool that we developed seems to work for this relatively more convoluted case. But when I want to express my solution, the entire process becomes a little bit dirty, it becomes a little bit complex. So now what I want to do is, I want to use some sort of a shortcut that my tool gives me. Now if you could recollect the analogy that we used for introducing the tool, we said that this tool or building a tool is nothing but we want to know the places that surround our home. We just don't want to know the route from our home to work or from a home to our class or from our home to playground. We want to know all the routes that surround our home, so that if we are lost or if a route gets a bit more difficult, we want to take an alternate route. So that is exactly what we are going to do here. We know the route, we know the tool, but we see that the tool or using that particular tool, the problem becomes a bit more complex, it becomes convoluted. So we are now going to take a shortcut. Now you might think that this shortcut is not totally allowed in the context of mathematics, and these shortcuts are not always the right way to go about. If you are so strict and if you are along those lines of thought, maybe this session could be a surprise for you. Maybe the subsequent discussion might be a surprise for you. Just consider it and see if you agree. Now, this expression here, the original problem statement that we would like to solve, this entire expression here, can be rather could be rather treated as a parent expression for one of the problem that we solved in our previous discussion. The problem that we are considering can be stated as a generalized case for one of the problem that we consider in our previous discussion. In our previous discussion, the force was dependent on position. Now in this case, the force depends on both velocity of the atom and also the position of the atom. So it is rather a more generalized case of what we considered in our previous discussion. Now what we are going to do, the shortcut, what we are going to do is, generally the tool allows us to understand the form of the solution and begin with that. So when we consider the approach of the tool, we understand the form of the solution and we make the assumption that the solution is smooth. Now in this case, what we are going to do is, we are going to take a step further, and instead of just assuming what is the form of the solution or just understanding or starting from the form of the solution, what we are essentially going to do is, we are going to directly and daringly going to assume the solution itself. Now we might think that this is not so conventional and this is not accepted and it will not be successful. You might be of that understanding, but luckily for us and fortunately for us, we have an entire book that is written just to vindicate this approach here, this short route here or this shortcut here. So if we are able to make an educated guess, then of course, and we will be able to come up with the actual solution, a solution that is more approachable from that educated guess. Now as the name of the book indicates, so this here is an actual book. I guess this is available, so maybe you can look it up. So this is an actual book. Now the primary goal of this book is not to rather enjoy the math behind solving a given problem, but to arrive at the problem. So as you can see, the book is wonderfully named as Street Fighting Mathematics, of course written by an Indian. So in street fighting, even if you are someone who enjoys, say, the combat, the art of the combat, you enjoy every move that is involved in the combat, that is not something that is valued in a street fight. In a street fight, you have to, in one way or the other, you have to knock the other person out. So even though you are a person who enjoys the art of combat, in case of street fighting, all you are interested is in the results. So the same applies for when you are using mathematics in the context of engineering or in some physics problems, wherein you are more interested in the solution rather than that of the beauty that you would find while you are arriving at it. Of course, that is something that mathematicians would admire the most, because they do something called as math qua math. So this qua is something that it's a Greek term, I guess. So meaning you do math for the math's sake. You want to enjoy every step that is involved in the derivation. You want to see the beauty of it. Of course, you can even solve this problem here using the previous tool, using the tool that we have developed, and see how the terms get associated with one another, how one thing cancels out the other, how you would be able to make some meaningful simplification of this solution. Of course, all of that is possible. So that's what we mean by math qua math, meaning doing math for its own sake, admiring each and every step. But I don't think this is the right setting for it, and you guys are the right audience for it. Of course, if you are teaching it for some budding mathematician, they might enjoy it, but unfortunately, we are interested in the solution. So therefore, we are not here to enjoy the beauty, but we are in the street and we are trying to win the problem. So what we are going to do is we are going to assume our solution. So again, it's just not randomly assuming, we are going to make an educated guess of our solution. So the educated guess, to make the educated guess of our solution, let's consider this a specific case of this generalized problem here. So what you essentially have is this expression can be written as the double derivative of the function is in a way equal to that of the function itself. So basically, when you can rewrite this term here, rather the one of the simplified cases of the original problem as something like this, wherein the double derivative of the function is rather equal to that of the function itself, of course multiplied with a constant. Now we are rather exposed to different functions in our preceding courses in our school days. So we can think of one function that will satisfy this condition here, which when differentiated twice will go back to its original form, or will assume or will resume its original form. So one of that function is nothing but e power x. So I can assume my solution to be e power x, because when I take the second derivative of e power x, I still end up having my e power x, like in this case here. The first derivative will give me e power x and the second derivative will give me e power x. So I'm writing e power x is exp. So this is the form I adopt to write my e power x. So it makes my job much easier, or this is part of if there is one language wherein you express your e power x in this way, I'm just adopting it. Nonetheless, so I assume my solution, just not the form of the solution, but I assume that my solution is e power delta x. So in this case, I'm assuming my solution is e power delta x, just because the solution, at least on the surface, satisfy this equation here, or the equation here, meaning even if I take the derivative of this function here, this function remains the same. The first derivative has the same form, the second derivative also has the same form. So now that I have assumed my solution, I can take the first derivative of the solution, and also I can take the second derivative of the solution. Now I see the form of the problem that I have to deal with, the form of the equation that I have to solve. I make an assumption with my previous understanding, with my previous knowledge, a priori knowledge. So, and then I consider the first derivative of it, and then consider the second derivative of it. Now I will be able to substitute both of this into my original expression here. I'm substituting my first derivative, second derivative, and original assumed solution into my original problem statement. Then my problem statement changes to something like this. Now of course I could rearrange this, and I will have an expression like this. Now this will be possible only when this term here is equal to 0. So this is what we refer to as the characteristic equation. So when this condition is satisfied, then, and if I'm able to find a delta from it, then I know what my solution is going to be. So a quick recap. In our tool, we start with the form of our solution, which is usually f of x, and we assume that it is smooth. In the shortcut, in the street fighting way, we directly assume our solution based again on the nature of the equation that we would like to solve. And when we do that, we end up assuming the f of x is e power delta x. We take the first derivative and second derivative, substitute into our original problem statement, end up with an expression like this that gives us the characteristic equation. Now this is nothing but a quadratic equation. We can adopt a form or an equation to solve this, or a solution. We have a formula to solve this, like what we see here. This is something that we could Google it up, or you remember from your school days. Now you have a solution with delta, the prefactor that is associated with x, and that is d. Even though now we have taken this approach, we have assumed a solution, and now we have arrived at the one unknown, that is delta, which is plus or minus d. This gives us, this completes our attempt to solve this equation here. There is one problem that this form of solution presents. That problem is this unknown delta can assume either plus d, or it can either be minus d. It can be plus d, it can be positive d, or it can be a negative d. Now, had it been rather a purely abstract mathematical problem, we don't have any problem with, or this is not a big issue, because of course it is possible to have two solutions, plus and minus. But unfortunately for us, we are dealing with a physical scenario. We are dealing with something that happens in our real life situation. We are dealing with our physical system, and each and every term, it means something that is physical. And when you have something that is physical, very rarely we see, at least in the non-quantum world, very rarely we see that two things being true at the same time. So either if we solve for this expression, and this ultimately will give me the position of the atoms, either my atom can be here or it can be here. Let's say my position gives me, my plus d gives me this, and my minus d gives me this. Both of this cannot be true at the same time. Either this is true or this is true. Now this is something this approach of solving the problem presents us with. So even though on the surface of this might look trivial, but when you understand that all that we are solving is associated with the real life, the physical world, then this is rather something that needs to be addressed, and this is rather something that cannot be easily just waved away, or rather shoved under the rug. So we need to address this. Now one way of addressing this could be, we can impose a statement saying negative answers are not allowed in the physical world, so we have to go just with the positive answer. I don't know how far it will be applicable in all the physical instances, but one real solution that we could adopt, that is again founded in the mathematics, is that we can consider the nature of the expression we have solved, and then express the solution in such a way that is consistent with the original problem statement. Let me repeat. We take an approach, we take a short route. And as always, even though the route is short, it doesn't mean that the solution is going to be easy. We took the short route, even though the solution appeared to be easy, the end point of it has two terms, meaning we have two different solutions for one problem. So that is not always possible, particularly when your problem is with the real life. So we need to have only one solution. One thing you could do is ignore the one of the two solutions, but that is not always the right thing to do. So therefore, we are using another approach which is consistent with the nature of our original problem statement. So this is our original problem statement. This is the original expression that we would like to solve. And if you consider the form of it, this is referred to as a linear ODE. So here we are qualifying our second order ODE with another term which is linear. So when you have a linear ODE, and the linear ODE has two solutions to it, it is an axiom that, or it could also be proved that, the sum of these two solutions are also the solution of this ODE here. So let me repeat. When you have a linear ODE, and the linear ODE offers you two different solutions, the sum of these two solutions is also a solution of the ODE. So it means I can sum up this plus d and minus d with, or substitute my plus d and minus d in my original solution. My original solution is this. I can introduce plus d and minus d in the place of my delta or rather lambda, and then I can sum this two up. That will give me my solution, and this is only possible when I have a linear ODE. So when I do that, instead of considering these individual terms, I consider its sum and treat it as a solution, then my solution would look something like this. So of course, we have introduced the term linear, and this linear is just the nature of the original equation that we are solving. Maybe if time permits, we will have a separate session to distinguish the linear from non-linear. We will play around with it to get a better understanding of it. But since this is something that reflects what we experience in the real life, and this, fortunately for us, happens to be linear, then this dilemma here can be solved by considering the linearity of it. So we take the sum of the solution and we end up having a solution of this form here. So my solution now not only includes my plus t, but it also includes my minus t, and these are k1 and k2 that is associated with, or the proportionality constant that are associated with my relation, and the relation that involves plus t and my minus t. Now the question still remains, how will I be able to find? So my d is the solution, my x is rather the fundamental variable, so I can write my x can be treated as my t, and d is the solution that I get out of my by solving this expression. Now then there is one or two other parameters that still remain unknown, meaning we don't have any significance or any physical significance for our k1 and k2. Now how could we arrive at, or how could we find this k1 and k2, which we don't know? Of course, even though these are proportionality constants, we don't know what these two are. Now how can we calculate this? So one good way of calculating this would be substituting my f of x as 0. So that would give me, if I substitute my f of x as 0, then I would have a term f of x of 0 will be equal to my k1 plus k2. And then I can take the first derivative of it, of my solution f of x, and that will be my, I take the first derivative of it, and I also know my d values, then based on that I will have an expression for k1 minus k2. The d's are known, the d values are known. I take the first derivative and I get my minus sign introduced. So I will have an equation for k1 minus k2. So based on the initial condition that is associated with my velocity, so this will be my velocity initial condition, and based on the initial condition associated with my position, so at time t0 what is my velocity, at time d0 what is my position, I will be able to come up with an expression for k1 and k2, so that I will be able to substitute here. So all the terms in my final solution will have significance and will have a definite value. So basically the tool works, but the tool gives us the route the tool takes is extremely complex. So we take a short route. Short route gives us an easy solution, but even though the short route is short and it is easy, the solution that it gives has a bit of a complexity associated with it. So we go back to the nature of the original problem that we are solving. That gives us a way out. So instead of just considering the solution offered, we take the sum of the solution and come up with the solution that is f of x. So this is the individual solution for the characteristic equation. Sum it up, we get the overall solution for our problem. So f of x, the overall solution for our problem, is now of this form here. Now we know what is d, we get it from the characteristic equation. This gives us our d. We don't know what k1 and k2, so in order to find what k1 and k2, we consider the initial velocity, my velocity when my time is 0. So f dash of x when my time is 0. So this is what is my initial velocity, and we also consider our initial position. So when I consider my initial velocity and initial position, I will have two different equations involving k1 and k2. Two unknown, two equations. I will be then able to arrive at values for k1 and k2, thus solving this problem here much more efficiently. So the shortcut, even though seems to bring in an issue, we have our original equation to help us out, and now we have arrived at a solution. So with this, this lecture has taken a time a bit more than what our usual session is about. But still, I would want you to review this with some, I would want you to take some time to review this a bit, so that you understand why do we have two terms for this solution here, and how we are able to find the coefficients of these two terms, that is k1 and k2. So with this we will wind up this lecture, and we will see if this tool will be helpful and if this shortcut will be helpful for other complex expressions. Goodbye.